Hello everyone, this is Shovik and you are watching college level physics. Today I'm going to talk about some basic and important aspect of stellar spectroscopy. So let's get started. The contents which I will be covering today are listed here, as you can see. Now come to the importance of spectroscopy. Now, spectroscopy is a scientific technique of studying objects and materials based on the color of the object. It is one of the most important part of astronomy and astrophysics. Everything we know about stellar composition, temperature, pressure, density, speed of astronomical bodies like stars, planets, and galaxies comes by studying their spectra. It can also be probed to find atmosphere of other distant exoplanets, the chemical composition of nebulae, and the surrounding atmosphere of black holes, and many more. So let's move on to our next slide, which is the types of spectra. Now, there are mainly three distinct types of spectra: continuous spectrum, absorption spectrum, and emission spectrum. Now, continuous spectrum contains all wavelengths emitted by a hot, dense light source. As you can see here, wait for a minute. I'm choosing the laser point. As you can see in the first graph, this is the brightness versus wavelength, a graph of the light emitted by the source, which is here is the star. And this is the continuous spectrum. As you can see, no dips or peaks are present here in this graph or spectrum. And the second one is the emission spectrum, which shows the colored lines of light emitted by the glowing gas, which is here the cloud of gas. And as you can see, these are the peaks and which are emitted by the minerals or elements present in this cloud of gas. And the third one is the absorption spectrum, which shows the dark lines or gaps in light after the light passes through this cloud of gas. And you can see the pattern or the these valleys are present in the continuous spectrum, which are the signature of the different elements present in this cloud of gas, which absorbs the light emitted by the star, and then when it emits, we get the emission spectrum. So now let's move on to our next slide. As you can see, this is a artistic illustration of a picture of a spectrum. This is not a real one, but anyhow, these dips are due to the hydrogen atoms. And as you can see here, this is also the brightness versus wavelength curve, and the peaks and valleys are level with the elements and compounds that cause them. And as I have said earlier, that this is due to the hydrogen atom's presence in the stars or the cloud of gas. Now, these spectra are mainly produced by atoms and molecules. So now let's move on to our next topic, which is the atomic spectra. Now, in atom, the transition occurs mainly due to the electronic jump in different energy levels. Imagine Bohr's atomic model, like this model. When the atom jumps from this level to this level, it emits some radiation, which we call light actually. If it's fall on the visible spectrum, we see it. If it doesn't, we don't see it from our eyes actually, we observe it in different instruments. But anyhow, so we can see distinct line spectrum in each atom, but for molecule it's different, as we will see later. But here, this is the absorption spectrum of sodium atom, and this is the emission spectrum. As you can see, these two are the complementary to each other. And the second one is the due to nitrogen atom, the third one is hydrogen, and the fourth one is oxygens. So let's move on to the next slide, which is the molecular spectra. Now, there are three distinct types of transition in molecules: pure rotational transitions, vibrational transitions, and electronic transitions. Now, this is a schematic diagram showing how the transition occurs. Now, these two curves are called the Morse potential, and when electron jumps from this curve to this curve, it is called the electronic transitions. And it falls in the optical or ultraviolet regime of electromagnetic radiation. And these horizontal lines are due to the vibrational motion of the molecule. And when the transition occurs between these two levels, we call it a vibrational transition, which it falls in the infrared regime. And these tiny horizontal lines, as you can see here, I'm pointing, this is due to the rotational motion of the molecules. And when the transitions occur between different levels of this rotational motions or the rotational spectrum, we call it the rotational transitions, and which falls in the microwave regime. So, and this is a GIF of a particular element. I can't recall now. But here you can see these atoms are jiggling and vibrating and also having some rotation, but you can see here the electronic jump. But anyhow, this is a beautiful illustration as I have found on the internet. So now on to our next topic, which is the HR diagram or the Hertzsprung-Russell diagram. Now, this is the famous Hertzsprung-Russell diagram, which is the plot of temperature versus luminosity of stars. Now, depending on its initial mass, every star goes through specific evolutionary stages dictated by its internal structure and how it produces energy. Each of the stages corresponds to a change in the temperature and luminosity of star, which can be seen to move to different regions on the HR diagram as it evolves. Now, this reveals the true power of the HR diagram. Astronomers can know a star's internal structure and evolutionary state simply by determining its position in the diagram. So now move on to our next topic, which is the stellar spectral classification. How do we classify the spectrum of different stars? Now, we can classify different types of stars based on their surface temperature. Now, there is a famous mnemonic stating that O be a fine girt kiss me, where O denotes the hottest temperature star, and as we go along, where M denotes the coolest star. And for example, our sun is a G2b type star, which falls around in this region in between G and middle of the K. So this is how you can remember the temperature of star, where O is the hottest and M is the coolest. It gradually decreases from O to M. So now move on to the next topic, which is SAHA'S ionization. Now, if I don't include this topic, SAHA'S ionization equation, this presentation would be incomplete. As you all know that Saha was the first scientist to give a proper explanation of what causes the spectral lines of star, for which we call him the father of stellar spectroscopy. Now, this is the famous SAHA'S ionization equation actually, where I have put the values of the different constants and get this particular value, and here I have written down this particular variables, where n is the number density of ions, and n is the number density of neutral atoms, and T is the temperature, Ui is the ionization energy, and Kb is the Boltzmann constant. If you put this values depending on which stars you are looking at, you will get the number density of ions present in those stars, the abundance of different elements present in those stars actually. So finally, this equation is one of the basic tools for interpretation of spectra of stars in astrophysics. By studying the spectra of various stars, one can find their temperature, and from that, using SAHA'S ionization equation, determine the ionization state of various elements making up the star, as I have said earlier. So we can find spectra of various astronomical objects like stars, galaxies, nebula, exoplanets, black holes, quasars, and many such objects. And we will see some of them. Like, if you probe into a star surface, you might get this type of spectral image, but it varies from star to star depending on what kind of star you are probing in, what kind of elements are present in those stars. And if it's hydrogen present, you will see this types of spectra, and if helium, this types of, and so on and so forth. So now this is the schematic picture taken by the JWST, which is the composition of gas around active black hole in the interacting galaxy called Stephan's Quintet. Here you can see different types of elements present in the accretion disk of the black hole, which is nothing but a star falling or crashing into this black hole, and you can probe the surrounding atmosphere where you will get this kinds of spectrum, from where you can find the presence of argon, iron, neon, sulfur, and oxygen, and many such elements. And here you can see the molecular hydrogen silicates are also present in this particular surrounding of the black hole. So now move on to the next slide, which shows the chemical composition of a distant galaxy behind SMACS 0723, which was captured by NIRCan of JWST. Now this galaxy was formed in the early universe around 13.1 billion years ago actually, and if you probe into the details of this galaxy, you will find this kind of spectral image, and from where you can get the information that oxygen, hydrogen, neons are also present in this galaxy formed in this early universe. So this is very exciting news actually. Now the next picture you are looking at is the atmospheric composition of hot gas giant exoplanet called WASP-96b, where you can see the presence of water molecule, which is a very exciting news actually. As you know, water is an essential component of life, so finger crossed what we found next. So this is the spectroscopy animation of Southern Crab Nebula, and here, if you probe at the center of this nebula, you will find the spectral signature of different elements. For example, if you see here, this is the presence of oxygen, and this is due to hydrogen. Next comes the nitrogen, and finally the sulfur. So if you use different kind of filters, you will notice the presence of these kinds of elements. So next, move on to our final topic of today's discussion, that is the spectrograph. Now, a spectrograph is an instrument used to obtain and record an astronomical spectrum. The spectrograph splits or disperses the light from an object into its component wavelength so that it can be recovered and then analyzed. Now, this is the most basic and simple of kind of spectrograph, which uses only a prism. As you all know, this is a CFL lamp, and this is actually an LED lamp where the prism splits this light into its multiple wavelength, and you can see this pattern. You should actually try it at your home if you have one, this prism. So this is a bit advanced spectrograph, and this uses the diffraction grating, and as you can see, the light is falling through this slit into the mirror, and this mirror focuses that light into this diffraction grating, where this diffraction grating actually splits the light into its multiple wavelength or component wavelength, and this mirror actually redirects this light into the photo detector, through which it goes into the computer, and then we analyze the data. So this is how basic spectrograph works. So what we have learned today? What is the summary of today's discussion? Now, so we can see that stellar spectroscopy is one of the most important branch in astrophysics, whether measuring temperature of star, chemical composition of different astrophysical bodies, exotic environments of the black hole, and much more. So thank you for watching this video. Take care and goodbye. See you then. Bye.